Welcome to an interactive course designed to validate and improve our knowledge of heat treatment. The topic of this course is an explanation of the issue of steel carburizing. There are a large number of steel surface treatment technologies aimed at changing the properties of the metal surface compared to its usual properties. The most well-known include carburizing, nitriding, and nitrocarburizing, induction hardening, and the less frequent ones are surface hardening by flame, plasma, laser, electron beam, ion implantation, or PVD and CVD coatings. All these technologies differ both in the way the layer is created and in the affected depth. In some cases, it is millimeters, but in others, it is only microns. As can be seen in this graph, in the case of carburizing, it is a range of usable depths from 0.2 to 5 millimeters. The opposite is ion implantation, where we can talk about depths up to 1 micrometer. In terms of development trends, carburizing occupies the largest space. So what is it? Carburizing is the process of saturating the surface with carbon at temperatures corresponding to the austenite temperature. Carburizing takes advantage of the fact that hypoeutectoid steels with a low carbon content 0.1 to 0.2% and a high proportion of ferrite are soft and tough after hardening. However, if the surface of the steel is saturated with carbon to a certain depth, usually to a eutectoid point, concentration of 0.8%, then this surface after hardening is very hard, on the order of up to 65 Rockwell. We thus obtain a tough core with relatively high strength and high toughness, and at the same time a very hard and wear-resistant surface. To ensure the carburizing process, we need to heat the parts to the austenitization temperature, and we need a source of carbon. Since case-hardening steel has a very low content of this element, the carburizing temperature will be high according to the iron carbide diagram, above the A3 temperature, usually between 900 and 1050 degrees Celsius. The carbon source can be a carburizing salt, gas, or liquid. However, since carburizing salts are based on cyanides, this technology is on the decline due to environmental problems. The same applies to the liquid, when dripping kerosene or acetone into the carburizing furnace was usually used. And we can almost forget about this technology today. At present, but also in the near future, it is mainly gas carburizing and low-pressure carburizing that are taking over and developing this role. In case of gas carburizing, we can speak of carburizing at atmospheric pressure. A typical environment is an endoatmosphere, or a nitrogen-methanol atmosphere as a basic gas, and a carbon carrier is added to them, like natural gas, acetylene, ethylene, propane, or methane. Carbon suitable for diffusion is released based on a chemical reaction between the individual components of the atmosphere and the steel surface. In the case of low-pressure carburizing, known by the abbreviation LPC, pure gases are then used at low pressure up to 10 millibars in a vacuum furnace, such as methane, acetylene, propane, ethylene, or their mixture, and carbon is created here by thermal decomposition of the gas. Optimal properties of the carburized layer can be achieved if the steel surface is saturated from the original 0.1 to 0.2% carbon to the eutectoid composition to 0.8% carbon. We must therefore be able to control the carbon potential in the furnace in such a way that this is achieved. The same principles apply here as we explained in the course on hardening under a protective atmosphere. There are three basic methods for measuring the carbon potential CP. These are measuring and controlling CP using the dew point, infrared analysis of CO2 in the atmosphere, and today the most common solution, measuring and regulating CP using an oxygen probe. For the hardening process, the carbon potential of the atmosphere should be in equilibrium with the carbon in the steel. If this were the case, however, neither decarburization nor carburization would occur. We do not need this in carburizing. On the contrary, the goal is to change the carbon in the steel, and we therefore need the atmosphere in the furnace to have a carburizing effect. But we don't have to worry about the actual measurement. For each measured value, there are already developed curves showing the dependence of the carbon potential on the dew point, on the CO2 content, or on the size of the signal in millivolts from the oxygen probe. Based on these, the instruments then evaluate whether more or less added hydrocarbon is needed in the case of the endoatmosphere, or hydrocarbon and air in the case of the methanol atmosphere. The dew point, or CO2 measurement, is carried out outside the furnace on an atmospheric sample taken from the furnace, while the oxygen probe is inserted directly into the work area, and thus measures the carbon potential directly in the furnace. The furnace atmosphere, whether endo or nitrogen methanol, provides us with the basic potential of the atmosphere. The addition of hydrocarbon then sets the potential required for the formation of free carbon for carburizing. We must be able to distinguish between two different problems. The first is the formation of free carbon and its transfer from the atmosphere to the interface with the metal surface. The second problem is the propagation of the carbon thus obtained inside the steel by diffusion processes. Therefore, in order to prepare the carbon for its own diffusion, we must create it in atomic form. Only in this way are we able to get it into the iron lattice, to austenite. Only atomic carbon has a size that allows it to occupy interstitial positions in the austenite lattice. But not all carbon formed in the atmosphere gets into the steel. The amount of carbon transferred to the steel is tied to the carbon transfer coefficient beta according to the formula shown, and to the potential gradient between the atmosphere and the surface. Although our goal is to have the maximum beta value, since it depends, among other things, on the ratio between the hydrogen and carbon monoxide content in the atmosphere, it can only be controlled to a limited extent under the conditions of a conventional carburizing atmosphere with the addition of hydrocarbon. Therefore, if we need to increase the transfer of carbon to the steel, it is easier to increase the gradient between Cp and Cs by increasing the saturation potential Cp. However, when the steel surface is saturated to the level of iron carbide formation, according to the ACM line, and the steel surface can no longer accept more carbon, the flow of carbon into the steel stops due to the zero gradient between Cp and Cs, and soot is formed. Since the Cp value, which we know as the carbon potential of the atmosphere, does not actually express the chemical potential directly, but ability of the atmosphere to carburize the steel to a certain amount of carbon, this value is sufficient for us for the practical management of the carburizing process. We now find ourselves in a situation where we have carbon in sufficient quantity and form. Once it enters the crystal lattice of iron, it moves further only on the basis of generally known diffusion laws. The driving force behind the movement of a carbon atom is the gradient of its activity between 2 points in steel. The diffusion rate depends on the diffusion coefficient d, the gas constant r, the activation energy Q, and the temperature according to the formula shown. Carbon is then transferred mainly through interstitial positions or through vacancies. This means that it tries to occupy either between the atomic spaces of the crystal lattice or free positions in it, arising as a result of random lattice disorder. In order for an atom to occupy an interstitial position, its size must not exceed 59% of the size of the basic metal atom. To ensure the movement of a carbon atom, certain energy conditions must be met. One of them is temperature. With higher temperatures, the austenite lattice expands and the limiting energy required for the movement of an atom decreases. Higher temperatures therefore accelerate the diffusion rate. Lower temperatures slow it down. Because in the first phase of the process, the carbon gradient between the surface and the core is high, this phase of the process proceeds very quickly. For example, if we set the saturation potential of the atmosphere to 1.2% carbon, then according to the graph, this carbon concentration on the steel surface will be reached in 25 minutes. This will be approximately the moment when the difference between CS and CO will be the smallest. As the carbon concentration gradient subsequently decreases into the depth of the steel, the diffusion rate also decreases. This decrease has an exponential character. One of the consequences is that only under certain conditions can reliable carburizing be carried out to small diffusion depths of up to 0.4 millimeters. On the contrary, for large depths above 2 millimeters, the process becomes less effective and requires very long processing times. Diffusion does not occur at the same rate for all steels. The basic case-hardening steels are C15, 16, manganese chromium 5, 15, nickel chromium 13, or 18, nickel chromium molybdenum 7-6, or their equivalents. The first steel is purely carbon, with a certain portion of silicon and manganese. The second steel already has around 1% chromium and an increased manganese content, and in the third and fourth case, these are steels with additional nickel or molybdenum. However, precisely because steels have different alloys, the diffusion rate will be different and individual for each steel. This is due to the fact that alloying elements that form carbides usually slow down diffusion. This slowing down is caused by the binding of diffusing carbon to the atom of the carbide-forming elements. Once the carbon atom is captured in this way, it is no longer capable of further diffusion. This applies, for example, to chromium, manganese, molybdenum, or vanadium. On the contrary, some elements accelerate this diffusion, for example, silicon or nickel. With increasing amounts of carbide-forming alloying elements, the diffusion rate will therefore decrease. The highest diffusion rate will be achieved in steel C15, lower in 15, nickel chromium 13 or 18, nickel chromium molybdenum 14-6. This can be seen in this graph with specific steels. Our steel 16 manganese chromium 5 is not directly shown in the graph, but it is similar to the tested 17 chromium 3, only it has more manganese, an element that slows down diffusion. In the same way that the diffusion coefficient changes with the alloying of steel, the activation energy will also change. The more alloyed the steel is, the more energy the carbon atom will have to gain to change its position in the lattice. The result will be diffusion profiles according to this graph. The carbon diffusion rate corresponds to the assumptions. The most alloyed steels are on the left. The dashed curve corresponds to the iron-carbon system without other alloying elements. Only steel C15 will have a faster diffusion process. All steels alloyed with chromium, molybdenum, or vanadium are slower. Both 16 manganese chromium 5 and 15 nickel chromium 13. The effect of a chromium content of 0.2 to 2% can then be compared to a situation as if we are carburizing at a temperature 20 to 120 Celsius lower. Therefore, this fact must be taken into account when estimating the time of the carburizing process. Knowledge of material properties, in our case, the diffusion coefficient D, and the activation energy Q, allows in practice to model the carburizing process to a specific depth, optimize the carbon content in the surface, and also partially adapt the diffusion profile to user needs. However, the carburizing process is rarely carried out in only one period. This applies only to small CHD up to 0.5 millimeters. For higher carburizing depths, a two-phases process is usually used, where the diffusion period is included after the saturation period. The graph shows the temperature profile of the furnace when the batch is loaded into a heated, and carbon-saturated hot zone. At a high atmospheric potential Cp of 1 to 1.2, the steel is saturated with carbon. Since the carbon potential gradient between the atmosphere and the surface is highest at this stage of the process, the amount of carbon transferred is also high. In the next step, the potential is then reduced to 0.8 to 0.9. The temperature may also change, and the carbon in the layer is allowed to diffuse without new carbon dotation. The reduced mass flow of carbon from the atmosphere will mean a decrease in the carbon concentration on its surface, and it will gradually decrease to the eutectoid amount to approximately 0.8%. This is followed by quenching. In this step, the processes vary. It is hardened either directly from the carburizing temperature, from a lower temperature, corresponding to the new state of the steel after saturation, or the batch is taken out of the furnace, cooled, and then heated again to the new quenching temperature. We will come back to this later. The graph shows that we change the carbon potential up to 4 times during the process. Therefore, adequate measurement of Cp and flexibility in changing it are also needed. It should also be mentioned here that the requirement for the accuracy of the regulation of the carbon potential Cp is within the tolerance of plus minus 0.05%, according to CQI9. The result is on this chart. The diffusion profile after saturation with Cp 1.2% is shown in dashes, and the state after the application of the diffusion period is shown in a solid line. The impact of the carburizing process conducted in this way is unambiguous. If the carburizing process is completed, we still need to harden the carburized layer. But here is the problem. Since the initial concentration of carbon in the steel was 0.1 to 0.2% carbon, we had to go with the temperature to the range of 900 to 950 degrees Celsius, according to the iron-iron carbide diagram. These are usually up to 950 degrees Celsius, but in some cases they can be higher at temperatures, up to 1000 degrees Celsius. At the same time, it is necessary to take into account a possible increase in austenitic grain. There are a few ways to deal with this. The first method is hardening directly from the carburizing temperature. However, the result will be a rough martensitic structure. The reason for this is that the size of martensite is dependent on the size of the austenitic grain, and this increases at high temperatures. The second option is to cool the batch in the furnace to a temperature above AC1 after carburizing, usually to 780 to 850 degrees Celsius, better suited to the eutectoid carbon content, and then quench it. We get better structure and less distortion. The third possible way is to cool the batch below a C1 and then heat it again to a quenching temperature. However, how to do it in practice depends on the design of the furnace. In no case can this subcooling be carried out in the heating chamber because its safety temperature is 750 degrees Celsius. Below this temperature, the endo is turned off and the furnace is gassed. In the case of a one-sided furnace, the batch is transferred to a cold chamber, which is still under a protective atmosphere, cooled down and returned to the heating chamber. However, we cannot do this with a double-sided furnace. The batch must be taken out of the cold chamber, transferred to the other side of the furnace, and reloaded back to hot chamber. In this case, however, we are already talking about option 4, where we let the batch cool down in a cold chamber below martensite start temperature, usually below 300 degrees Celsius, put it back in the heating chamber and heat it to a quenching temperature according to the saturation of the layer. The last variant is the so-called layer and core hardening. After carburizing, the batch is removed from a cold chamber, heated again to a temperature according to the carbon content in the core, to 900 to 950 degrees Celsius, and quench. Subsequently, the batch is washed and heated again. this time to a temperature corresponding to the amount of carbon in the layer. However, since the material will no longer be fully austenitized in the core during the second quenching to a lower temperature, the structure will contain a greater or lesser amount of ferrite. This can have a positive effect on the toughness of the component, but with regard to double quenching, greater deformation can be expected. The way we actually implement the process depends not only on the structural requirement, but also on the processing cost. If we consider the direct hardening process from the carburizing temperature as a reference with a value of 1, then all other variants will mean a process longer by 10, 30, 50, and 80%. In the case of working with the Ipsen TQF7 double-sided furnace, we can consider an average batch in the process of 280 kilograms. If we have carburizing to the most common depth, 0.8 to 1.2 millimeters, then we can count on a price of 1.6 euros per 1 kilogram of carburizing as the average market price. The selling price of the process will therefore be 448 euros. The graph shows how the individual options affect the processing costs. Logically, the option with direct hardening appears to be the cheapest. However, it is rejected metallurgically due to the growth of austenitic grains and, as a result, coarse martensite. Another option is to cool to a quenching temperature corresponding to the amount of carbon in the layer, namely 780 to 850 degrees Celsius. Although this option is usually 10% longer in time, we still have a good profitability of the process. Option 3 will be valid for a single-sided chamber. In this case, after carburizing, we transfer the batch to a cold chamber. Let it cool below AC1 at least below 723 degrees Celsius, but usually to an even lower temperature, and then return it back to the heating chamber to heat to the quenching temperature. In this case, we can expect the process to be 30% longer than in option 1, and the profit from the process will be close to zero. However, the situation is worse for a double-sided chamber. After cooling, the batch must be removed from the furnace, and therefore, in order not to oxidize the surface, we must cool it below 450 degrees Celsius. This requires a longer time for both cooling and reheating. If in variant 3, the processing time is 30% longer, then in variant 4, it is 50%. We are losing money with the processing. The worst situation is in variant 5 with double hardening. As we have already mentioned, this type of hardening of the carburized layer to the core and to the layer is characterized by the fact that we harden twice. The process time is already increased by 80%. If we apply the market price, then the loss of the process with CHD 0.8 to 1.2 millimeters will be 31%. So we have to go up with the price. At a price of 2.3 euros per kilogram, we will be at zero. Only at a price of 2.76 euros per kilogram, we will have a 20% profit per process. However, this price is 72% higher than the market price for this carburizing depth. It is therefore necessary to negotiate with the customer whether the choice of the optimal structure is economically feasible. The amount of carbon in the layer also affects the hardness after quenching. The graph shows that the maximum is achieved when the surface is saturated to approximately eutectoid composition, in the range of 0.6 to 0.8% carbon. Above this value, with increasing carbon content, the hardness decreases due to the increasing content of residual austenite. The second factor affecting the hardness of the layer is the content of alloying elements in the steel and their type. In general, this hardness increases slightly with the content of chromium and molybdenum or manganese. This is due to the fact that with these alloying elements, the amount of hard carbides formed by them also increases. On the other hand, nickel or silicon change this hardness only minimally. At the same time, however, these elements affect the temperature of the eutectoid point. Nickel and manganese reduce it. Chromium, silicon, and molybdenum, on the other hand, increase it. But molybdenum in steel has another effect. The picture shows that this element stabilizes the hardness after carburizing and tempering. The amount of carbon content also affects the behavior of the lines for martensite start and finish. With its increasing amount, we are approaching zero temperature with the martensite finish curve. The graph shows that even at a concentration of around 0.4% carbon, we cross the zero temperature value. It follows that either we have to take into account a certain amount of residual austenite for carburized layers, or we have to complete the martensitic transformation by cooling it to the area of negative temperatures. The problem is already the detection of the amount of residual austenite. It is detectable by optical metallography at a content greater than 10 to 15%. Below this limit, it is necessary to use the X-ray diffraction method. Its weakness is that the X-ray beam has a penetration depth of only 10 microns. In some cases, the method of magnetic induction or Mossbauer spectroscopy can be used, distinguishing between magnetic and paramagnetic components in steel. In both cases, the detectability of residual austenite is from 0.5%. The figure shows an example of an X-ray diffraction record for a residual austenite content of 9.6 plus minus 1%. If we did not reduce the amount of carbon in the carburized layer to the level of the eutectoid point, there would be a problem according to this diagram. With increasing carbon content, the content of residual austenite in the layer increases significantly, in extreme cases up to 40 to 50%. This can be seen in this metallography of the carburized layer. The entire area below the surface shows significant oversaturation and a large amount of residual austenite. This results in a decrease in surface hardness. Here we can see how the residual austenite affects our mechanical properties. Tensile stress is plotted on the vertical axis, proportional elongation on the horizontal axis. The graph shows that with a residual austenite content of 35%, the yield strength drops to 50% of the original value. This can already be critical for some applications. In terms of mechanical properties, residual austenite does not always have a negative effect. Due to its properties, such as higher ductility, it can contribute to better low cyclic fatigue strength in some cases. But these are exceptional. Its biggest drawback is that it is not stable and will gradually transform into martensite, although this can be over a long period of time, on the order of weeks. However, since the transformation of residual austenite brings about a dimensional change, all structures containing residual austenite will gradually change their dimensions. Since the crystalline lattice of martensite is larger than austenite, this spontaneous transformation will be accompanied by an increase in volume of 4 to 5%. Thus, the dimensions will change. But at the same time, this increase in volume will generate high internal stresses, which in some cases can initiate catastrophic cracks. From this point of view, where we have a clear goal in terms of dimensional stability or precisely defined mechanical properties, it is necessary to suppress the amount of residual austenite below 10% or even lower. Therefore, we need to consider the martensitic finish line and try to end the martensitic conversion by cooling it below zero temperature. The AMS 2759, Part 7 standard, then states that the permissible value of residual austenite is up to 10% for Class 1 parts and up to 20% for Class 2 parts. If the residual austenite content cannot be well interpreted metallographically, X-ray diffraction evaluation is mandatory. Magnification of 1000 is prescribed for optical evaluation. 500 for intergranular oxidation, and 200 for evaluation of the core structure. A typical cryogenic processing process is shown in this figure. Once the carburizing and hardening are complete, the parts are washed and removed from the quenching oil, and then moved to the freezing facility, usually before tempering. Devices for freezing are of two types. Compressor cooling gives us a temperature limit of about -70 degrees Celsius, liquid nitrogen freezers up to -196 degrees Celsius. The first solution, compressor cooling, is sufficient to suppress residual austenite in the layer. The result can then be, for example, the content of residual austenite according to this figure. The abbreviation CHTB, carburizing, hardening, tempering, blasting, means that the parts have been carburized, quenched, tempered, and blasted, while the abbreviation CH, cryogenic plus hardening, means that a cryogenic processing step has been added. The analysis shows that after the standard process, we have 12 to 20% of residual austenite in the layer, and after freezing, then 6 to 10. Thus, the residual austenite content was reduced by 50%. In practice, freezing times usually range from 2 to 4 hours at temperature. However, since the decomposition of residual austenite and its transformation into martensite occurs only by carbon diffusion in the crystal lattice, these processes are slow, and this fact is further enhanced by the low freezing temperature. We cannot therefore expect to reach zero values. We would have to significantly increase the freezing time to times of 24 hours or more. A description of some details can be found in various specifications, one of which is AMS 2759, Part 7. It is a standard for the carburizing of parts for the aerospace industry. It says that the parts should be frozen to a temperature below -73 degrees Celsius for 1 hour per 1 inch of thickness. Freezing should be started no later than 2 hours after hardening. However, in the event that there is a risk of cracks in the case of parts with complicated shapes, it is allowed to temper to 150 degrees Celsius before freezing. However, if the parts cannot be frozen within 2 hours after hardening, then stabilization tempering is also allowed with a time of at least 1 hour at a temperature of up to 121 degrees Celsius. Tempering is also part of the carburizing process. Details can be found in e-learning course number 03.02 entitled Tempering in a Protective Atmosphere and in a Vacuum. However, there are other factors in this part of the process that need to be taken into account. First of all, it is the relationship between tempering, hardness profile, and the depth of carburizing. The figure shows the relationship between the tempering temperature and the resulting surface hardness in HRC. The blue curve indicates a decrease in hardness for carburized and quenched samples. The red curve for samples where cryogenic treatment at a temperature of -70 degrees Celsius was additionally applied. If we display the respective diffusion profiles depending on the different tempering temperatures, we see how the layer hardness, but also the diffusion depth, CHD, decreases with increasing tempering temperature. The criterion for the diffusion depth is CHD 550 HV1. This decrease is clear. For samples without cryogenic treatment, it is from 1.19 millimeters for a tempering temperature of 150 degrees Celsius to 0.79 millimeters for a tempering temperature of 290 degrees Celsius. This is therefore a decrease in CHD of 0.32 millimeters, which is almost 27%. For samples with cryogenic treatment, it is from 1.17 to 0.79 millimeters. The difference is therefore 0.38 millimeters, or 32%. From the diffusion profiles for samples with and without cryogenic treatment, it can be seen that they do not differ much. Freezing only slightly increases the maximum hardness in the profile due to the transformation of residual austenite into martensite. The influence of the tempering temperature is much greater. However, as seen in the first graph, there is a significant difference in surface hardness measured by the Rockwell method. The last graph shows the content of residual austenite in the layer. The graph shows that cryogenic treatment stabilizes the content of residual austenite at a value of approximately 8%, and this value does not change with tempering. For samples that were processed without cryogenic treatment, there is a significant decrease in residual austenite within temperature range of 190 to 250 degrees Celsius, from about 25% to 10%. Above this temperature, it does not change, but it does not fall below 10% either. What does this mean? The tempering temperature can reduce the diffusion depth by up to 30%, but we must take into account the prescribed surface hardness. So if our CHD is too high, then this is a way to correct the carburizing process if the requested depth was higher than required. If the opposite is true, and the CHD is lower than required, we usually have no choice but to include rehardening and, within this process, increase the carburizing depth by additional diffusion. However, we must be careful to set the CP in the furnace so as not to carburize or decarburize the surface layer with carbon outside the eutectoid point, 0.8% carbon. Another problem that we have to face in carburizing is internal oxidation. We cannot avoid this in carburizing processes in endo- or nitrogen-methanol atmospheres. The atmosphere always contains a proportion of water vapor or directly oxygen. Finally, the measurement of the carbon potential with an oxygen probe also indicates that oxygen is present in the atmosphere. Usually, oxidation is permissible to a depth of 10 to 15 microns, and on the drawings, this layer is defined as the property IOD, or internal oxidation depth. Details can again be read, for example, from AMS 2759, Part 7. Intercrystalline oxidation, according to this standard, should not exceed a depth of 13 microns on the unprocessed surface. If we oversaturate the steel surface so that we also exceed the solubility of carbon in austenite, another undesirable phenomenon will occur. Secondary cementite formations will begin to form. This phenomenon can occur especially when the surface is oversaturated and at the same time the steel is slowly cooled from the carburizing temperature to the quenching temperature. It is necessary to take into account the control of the atmosphere according to this graph, because the saturating ability of the atmosphere must not be overdone, precisely with regard to the possibility of precipitation of secondary cementite, or even worse, with regard to the precipitation of carbon in the solid phase in the form of soot. The AMS 2759 Part 7 standard limits the amount of secondary cementite to a maximum of 40% coverage of the grain boundaries in the layer just below the surface of the steel on the machined surface. But at the same time, it also says that large or angular carbides are not permissible. The individual structural components are then compared with the AMS Metals Handbook, Volume 9. An atmosphere that allows maximum carbon transfer to the steel has a high carbon potential, but at the same time does not exclude carbon in the solid phase in the form of soot, is considered optimal for carburizing. This diagram shows the dependence of carbon activity on the carbon potential Cp, or rather on the carbon content in iron. Soot begins to be excluded from the atmosphere when the carbon activity reaches the number 1. This varies depending on the carburizing temperature. For example, at a temperature of 900 degrees Celsius, this critical point is 1.2% carbon potential and increases with temperature to 1.5 at a temperature of 1000 degrees Celsius. This dependence essentially corresponds to the ATM line of the iron-iron carbide diagram and the supersaturation of austenite to the level of iron carbide formation. Not only are the components themselves at risk from excessive carbon content in the furnace, this also applies to the carburizing equipment itself. Excessive carbon exclusion in the form of soot significantly worsens the service life of the lining. The more carbon the lining absorbs, the more it loses its thermal properties, even becoming electrically conductive. As a result, damage can occur to the metal housings or the probe shell, since carbon supersaturation can lead to the eutectic point being reached and the material melting. The first picture shows an example of damage to the lining. The second shows the probe, and the third shows the melting of the radiant tube from the gas heating of the furnace. To prevent this, there are special procedures for burning furnace to rid the equipment of soot and excess graphite. For example, it is possible to raise the dew point of the atmosphere to 20 degrees Celsius by adding air and then maintaining this condition for 24 to 72 hours. The graphite in the form of soot in the furnace burns out. Another option is to completely remove the atmosphere from the furnace and burn the furnace in air only for 12 to 36 hours, with occasional opening and closing of the door. However, it is necessary to pay attention to the temperature inside the furnace. Burning carbon provides additional heat energy, and the furnace could easily overheat. If everything is in order, it is necessary to check what we have actually carburized. We adapt the carburizing process to what is prescribed on the drawing. This regulation is governed by the ISO 15787 standard, and it states that the carburized layer should be defined by the surface hardness and the effective depth. The figure shows the method of prescription. If the method is not specified for CHD, then HV1 is understood, and the effective depth is the depth where 550 hardness units are still achieved. For example, according to the American standard, it is 50 HRC. However, we can also prescribe other criteria. For example, according to this regulation on the drawing, we should carburize to a surface hardness of 700 Vickers units measured by the HV30 method. The effective carburizing depth should be 0.5 to 0.8 millimeters measured by HV3, and in addition, it is required that at a depth of 0.1 millimeter, the hardness is still 700 to 750 HV1. At the same time, it is specified that internal oxidation must not exceed 10 microns below the surface. The evaluation of the fact is usually then tied to metallographic inspection and hardness measurement. However, other methods can also be used, like wedge grinding or gradual grinding of the surface. Everything that is needed is contained in the corresponding standards. Usually, the entire measurement is automated. The device makes indenter impressions in the range and with the spacing specified by the user automatically, and then automatically evaluates them. It converts the results into a corresponding graphic record, which can then be printed as a certificate, proving that the CHD requirement has been achieved. In gas carburizing, special attention must be paid to masking, in case some surfaces of the component must not or can be carburized. Due to the penetration of the gas under atmospheric pressure conditions, it is very difficult to protect parts against carburizing with a protective metal sheath as we know it, for example, in plasma, nitriding, or carburizing. Therefore, two techniques prevail: copper coating protection and protection with special coatings. The copper coating protection process is described in AMS 2418. In some cases, there is also a layer of nickel under the copper layer to improve the adhesion of the coating. However, at high carburizing temperatures, especially in low-pressure processes, there is a danger of nickel diffusion into the steel. This can have the same effect on the surface as decarburization. The second method is various paint pastes based on copper or boron. However, it is necessary to distinguish the type of paint material because, for example, those containing copper are not suitable for carbonitriding due to a possible reaction with ammonia. On the other hand, pastes containing boron are now considered toxic substances and therefore require special treatment. For this reason, they can be considered in special cases. The thickness of the protective coating should vary from 0.2 to 1 millimeter and should not be thicker. Excess protective paste can also affect areas that should not be protected. Painted surfaces should usually not exceed 30% of the surface. Coatings should be applied to clean, degreased surfaces in one or more layers. Coating should be followed by drying of the coating for 3 to 8 hours, or this time can be shortened by drying at higher temperatures up to 100 degrees Celsius. The painted parts should be processed after the last coat within 24 hours. Most paints are removed after carburizing by washing in a water bath. There is an extensive range of protective coatings, for example from the German company Bergdorf, the American Dubois, or the French HEF Durferit. Finally, we will talk about the equipment used for carburizing. The equipment can be batch or continuous. Continuous equipment is usually not found in commercial heat treatment facilities and is more the domain of the automotive industry. Batch equipment provides lower capacity, but is commonly available and, above all, more flexible. Most of them are classic multi-purpose furnaces with single-sided loading or continuous type of furnace. A typical example of a continuous arrangement is the Ibsen TQF or Secco-Warwick furnaces. Single-sided loading is known in designs from Ibsen, IVA, or Ikelin. Another typical equipment is the Bell furnaces from Codere or Solo. However, in many cases, shaft furnaces that were manufactured in the 1980s or 1990s are still found. All of these devices operate on a similar principle, both in terms of the endoatmosphere and the control of the carbon potential. Only the control of the technology is at a significantly higher level. Here are, for example, control systems from Eurotherm, Protherm, or Supersystem, oxygen probes from Equinox, Supersystem, or Stange. It is also worth noting that according to the CQI-9 requirement, all furnace instrumentation must be based on digital data processing from 2023, not analog, if it is to work for the automotive or aerospace industry. And what are the most common defects in carburizing? First of all, it is insufficient surface carbon content in the layer. The layer will not have the required hardness and will be subject to higher wear. The reason may be, for example, too low a carburizing temperature or a low carbon potential of the atmosphere. We can see this in this graph, showing the relationship between carbon content in the carburized layer and surface hardness. However, if the insufficient hardness is only local, then it is necessary to check the washing process before carburizing and the method of removing oil residues and cutting emulsions. The problem may also be too great a depth of internal oxidation related to the length of the process or low tightness of the furnace. The opposite case is oversaturation of the surface layer with carbon. On the one hand, the layer will contain a high amount of residual austenite, and on the other hand, iron carbides and carbides of alloying elements will precipitate, reducing the toughness of the layer. In the picture on top, we have huge amount of residual austenite. In the picture below are the precipitated carbides. Their precipitation will occur as a result of oversaturation of the layer, while the batch is slowly cooled to the quenching temperature, or if the cooling rate in the oil is subcritical in terms of carbide formation during direct quenching. Another possible defect is decarburization of the layer due to an incorrectly set potential. The effect of decarburization is significant in that it reduces the compressive stresses in the layer, and in critical cases can change them to tensile stresses. In that case, however, the carburized layer will be susceptible to the formation of cracks in the event of their superposition with another source of tensile stresses. Therefore, this phenomenon must be avoided during carburizing. Also, a high temperature during carburizing in combination with a long time at temperature can cause a problem. Depending on the increasing temperature, the austenite grain will also grow and the martensite will become coarser, with an impact on the toughness of the layer. The figure shows an example of this phenomenon, the growth of austenite grain during carburizing at various temperatures from 900 to 1100 degrees Celsius. The course of carburizing is over. It includes my many years of experience and practice. However, the issues can be very complex and extensive and may not exactly match your experience. If you have any comments or suggestions for improving the course, please send them to the contact listed. My goal is for the courses to provide essential information for heat treatment employees at all levels so that they can continuously improve. The level of content is therefore adapted to allow both existing employees and new employees who do not have knowledge in the field to take part in this course. Based on these comments, I will improve and expand the courses so that they are a real benefit to everyone. As you have probably noticed, the course was not voiced by me, but by the great speech generator 11 Labs. Thanks to him, my English will also be understandable. So thank you also to Bill and his voice for his contribution to the field of heat treatment. What you saw as a video on YouTube is just a picture of what is created in Adobe Captivate as an e-learning course. It is available on my website, jstconsultancy.cz. You can access it for €20 for 1 week, €40 for 1 month, or €60 for 1 year. The course is created in HTML5 format. However, it can also be exported to SCORM 1.2 format, which stands for Shareable Content Object Reference Model. Other formats are possible for different LMS systems. You can order this form at my email address, and you will receive the complete course in HTML5 code and a perpetual license for €200 per course. The compressed zip file will be 50 to 200 megabytes in size, depending on the content of the course. You can then install this file in your corporate cloud or in Moodle LMS 5.0, on SharePoint or in the HR module of your ERP system, such as SAP, which can communicate with a learning management system, LMS, that meets the LMS specification. In this case, you will be able to prepare a training plan for each employee, including an evaluation of its implementation and success rate. Each course contains a test with many questions, and the output is a certificate of successful completion of the course. You can archive these certificates and use them for employee motivational rewards. The advantages of e-learning are obvious. The employee does not have to go anywhere. They can complete the course anywhere, on a computer, tablet, or even a phone, at work, on vacation, or even at home. And you will be sure that they have the necessary knowledge to understand what is happening in the heat treatment operation. I do not know of any disadvantages, so I just hope that these courses will serve you and be useful to you. And what is my vision for the future? You can see this in this process map. So far, 16 have been created in Czech and English, and I will gradually add new ones, depending on their importance in the life of the heat treatment operation. I don't know if the courses are perfect, but I'm sure it's a promising form of education that we shouldn't ignore.